Okay, we are now moving on to chapter 12, and we'll start real basic. We'll introduce the first two sections of chapter 12, which is all about area, and let you try some of the problems. So as we introduce some of the formulas, I'll try to show where some of the formulas are coming from, and then we'll do some example problems that go with each of the different formulas. Okay, the first couple of formulas are really basic. I know that most of you would know that the area of a square is just side squared, and the area of a rectangle is base times the height. Do a couple quick problems that go with that. The area of a rectangle is between 84 and 124 in this problem here, problem number 1. And so I know that it's length times width, or 8 times 5x plus 4. It's got to be between 84 and 124. And then I would just solve that inequality there. Basically, you would divide everything by 8, and then subtract 4, and then divide everything by 5. You're going to end up with an x value that's between 1.3 and 2.3. Two diagonals of a regular hexagon form a rectangle. So here's your rectangle, and you want to find the area of that rectangle if the side of the hexagon is 12. So this is 12. This is 12 here. I know it's going to be length times the width. I already have one of them. I already have the 12 here. So I got to just find the other piece of that. And so what I'm going to do here is I'm going to draw an altitude from here to here. It's a right angle. I know that each of these angles from one of our earlier chapters is going to be 120 degrees in a hexagon. So if this is a right angle here, I know this has got to be a 30-degree angle right there. 30, 60, 90 with a hypotenuse of 12. That makes us 6 root 3, as well as this will be identical to that 6 root 3. So it's going to be 12 times 12 root 3 is going to be equal to the area of the rectangle, or it's just going to be 144 root 3, and we can leave it like that in exact form. Okay, moving on to parallelograms and triangles. The area first for a parallelogram is equal to just the base times the height, where this is the base, entire bottom there. And where this comes from is if I take this triangle right here and I chop it off and I put it right there, and I attach it, I'm going to end up with just a rectangle, where this base is the same as this base that we had in the original diagram. And we're looking at just base times height. So that's why the area of a parallelogram is just the base times the height, and the height is the altitude. A triangle, which most of you know what the area is, so if I'm looking for the area of a triangle, most of you know the formula. But where the formula comes from is here's one triangle. I'm going to take the same triangle, I'm going to flip it over and attach it this way. So it's the same triangle, but just upside down. And what you have here is the shape of a parallelogram, where we know that's the area is going to be base times the height, but we don't want both of these triangles, we just want one of them, so it's going to be area is equal to half of the base times the height. And I'm going to flip over to the next page now and try some of these problems. Okay, on to page 2 here. We're looking at the back side where we have some example problems with triangles and parallelograms. As for this first problem here, 30, 60, 90 triangle. This side is going to be opposite the 30, this side will be opposite the 60, and so it's going to be base times the height divided by 2, or 1/2 of the base times the height, and so it's going to be the area is half of 36 root 3, or 18 root 3. Next one here, you have a right angle here. I could draw in an altitude like this and find that altitude. An easier way to do a problem like this, though, is to take advantage of this right angle here and know that I can make this the base if I turn my piece of paper a little bit sideways, and I can make this my height. And both, in this case, both of these are 12, so it's just going to be 144 divided by 2, or the area is going to be 72. For this next one here, it's an equilateral triangle. I can draw in an altitude. This is going to be 6, this is going to be 6, this will be 6 root 3, because it's a 30, 60, 90 triangle. And I can do 1/2 base times the height, or I'm going to get 36 root 3. So it's going to be half of 12, or 6 times 6 root 3. Now there's a nice little formula for equilateral triangles that's really useful. And the formula kind of works like this, where I have this is equal to the side, and this is equal to the side divided by 2, and this will be equal to the side root 3 divided by 2. And so it's just going to be half of the base is the side, so it's side over 2 times the height, which is s root 3 over 2, so it's going to be s squared root 3 over 4. And that's definitely a formula you'll want to memorize for future reference. Next one here is a parallelogram, and in this case the base is going to be 15. The height I can find. If this is 8, then I know this is 4. I know this is 4 root 3. And so it's just going to be base times height, or 60 times the square root of 3. This is the same type of problem where this is a 45, 45, 90. This will just end up being 9/2 root 2, like that. And you can just find the area from that. Okay, moving on to trapezoids. For trapezoid, what I can do here is I can kind of take one of these trapezoids from here, and I'm just going to flip it over and attach it over like this. Okay, so this actually, this base 1 is going to end up down here, base 1. This will be base 2 here. And the shape you're going to end up with is just the shape of a parallelogram. I didn't do a good job of drawing that there. But it's just going to be the area of a parallelogram, which is the base times the height. In this case, the base is b1 plus b sub 2 times the height, which is h. But I only want one of these guys, so I'm just going to take that and divide it by 2. And that's going to be the area of a trapezoid. Sometimes they define, folks will define the area of a trapezoid in terms of the median. The median is just the average of the bases. So in this case, the average of the bases is just going to be this portion right here. And so we know that sometimes they'll define it as the area is equal to the median times the height. Something to keep in the back of your minds there. The first problem here, talking about the sides of a trapezoid in the ratio 2, 5, 8, 5. So I know that I can draw in a trapezoid, and I'm going to just make each of these like in terms of x, because they're in this ratio here. So it's going to be 2x, 5x, 8x, and 5x again, which makes that an isosceles trapezoid. I'm going to draw in altitudes right here and here. That's a very common thing that we've seen in past with trapezoids. And so this is 5x, that's 8x. This again was 2x here, which makes this bottom portion 2x, which means each of these are going to be 3x and 3x, which makes these heights 4x. And so it says that the trapezoid's area is 245. 245 is equal to half of the bases added up, the sum of the bases. So it's just going to be 5x times the height, which is 4x. And then we can just solve this thing. X ends up being equal to 3.5. And I can just plug stuff back in to find the height and the perimeter of that trapezoid. All right, let's move on to kites. And there's a nice little derivation here. If I work with these guys separately, this one and these triangles separately, I know that the area of this kite is going to end up being, if I look at the red portion, let's take a look at the blue portion first. It's going to be 1/2 of the base, which is 2e, times the height, which is just c. I'm going to add that to the red portion, which is 1/2 of, again, 2e, which is the base, times the height, which is d. And so I'm going to end up with dE, which comes from here, and add that to CE. Factor out an E times D plus C. And so E is just going to be half of one of the diagonals. Let's call it diagonal 1. And this guy will be the other diagonal. D plus C is the other diagonal, diagonal 2. So the formula for the area of a kite is 1/2 of diagonal 1 times diagonal 2. And if I flip over to the next page, I'll try some example problems. Okay, moving on to the third page here. Let's do this one problem here. This comes up pretty frequently, where you have a rhombus. Now, interestingly enough, the thing about a rhombus is it's a parallelogram, but it's also a kite. So I can kind of use either of the formulas, and I also know that the diagonals are perpendicular to each other from our quadrilateral chapter. And if I have a perimeter of 68 here, that means that each of the sides is 17, and the short diagonal is 16, and I know the diagonals bisect each other, so this must be 8. It's an 8, 15, 17 triangle, so this is 15 and 15, this is 8 right there. And so to find the area of this thing, I can use the area of a kite, since it's a kite. It's 1/2 of the first diagonal, which is 16, and the second diagonal is 30, so it's going to be 240. Now to find the height of this thing, the height is the altitude going this way, and we also know the base is 17. Now, interestingly enough, we know the area is 240, so we can kind of back our way into this height using the fact that it's a parallelogram. So 240 is the area of a parallelogram, equals the base times the height. We know the base is 17, and we can find the height from that. So the height ends up being, if you want an exact answer, 240 divided by 17. And that'll be the height. I think I'll stop here and let you go ahead and try some of the problems, exercises from both sections 1 and section 2. All right, take care.